Hi everyone. I hope you have been following our series of the PMT classes. Today I'm going to be taking a topic in calculus called Pascal triangle and how to apply Pascal triangle. First of all, what is Pascal triangle? Pascal triangle is the increasing order of number as the series increases, depending on the coefficient or the quotient of a particular unknown coefficient. For example, x raised to the power 2, x raised to the power 3, x raised to the power 4. When it is to the power 4, you're going to increase the Pascal triangle to that level. So Pascal's triangle starts with 1. Then the next thing we are going to have 1. This 1 plus this 1 becomes 2. Then we have 1. See, now for us to build for power, this is for power 2. When we have power 3, we're going to have 1. 1 plus 2 is 3. 2 plus 1 is 3. And we have 1 here. So for the next one, we are going to have 1. For the power of 4, we are going to have 1 plus 3 is 4. 3 plus 3 is 6. 3 plus this is 4. And we have for the power of 5, we are going to have 1. 1 plus 5, 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And we have 1. And so on. That is how the Pascal triangle builds up. It increases according to the order of the power of increase. We're able to look at Pascal triangle. Now we're trying to look at derivative by first principle so that we can see how we will apply this to our topic of connecting the Pascal triangle to finding the derivative of a particular number. So if you are given x, y equals to x, then by first principle, the power of x is 1. So it is expected that should be literally written as y equals to x raised to the power 1. So according to the law of derivative, when you put dy dx, is this 1 is coming to multiply this 1x raised to the power 1 minus 1. So the power is coming to multiply the number that is standing with the coefficient, and then you are going to subtract 1 from the power. So from here, dy dx will be 1 times 1, which is 1x raised to the power of 0, which is x raised to the power of 0, and anything raised to the power of 0 is 1. So dy over dx is 1. So this is done by normal derivative. We have proven that. So we want to prove that this, if y equals to x, dy dx is 1. So let's use by first principle. According to first principle, if you have y, so we have proven this. So let me write down. We've proven this, that y, if y equals to x, dy over dx equals to 1. So we are going to prove this by first principle. Dy over dx is 1. So let's prove that this is correct. By first principle, when you have y equals to x, you are going to add dy to the left-hand side and add the x to the right-hand side. We are going to say y plus dy equals to x plus dx. So we want to find dy dx. So we leave dy on this side. We're going to take y to the other side when as a particular figure changes the quality sign, its sign will change. This is plus y. When it goes there, it becomes minus y. So we have x plus dx minus y. So, but recall that from our question, y equals to x. So we have dy will be equals to x plus dx minus x. So when this x goes with this, so dy equals to dx. So taking limit dx tend to 0, you are going to have dy divide both sides by dx. Divide both sides by dx. So dx cancel dx is 1. So dy taking limit dx tend to 0, dy over dx equals to 1. So we see we have proven that this equals to this. So this is applying them by first principle. By first principle, we were able to prove that if y equals to x, dy dx equals to 1. So this is by first principle. So I'm going to take another example for us to solve it and understand. All right, we were able to look at how to prove normal derivative and then proving it by first principle, and we saw that when y equals to x, dy dx equals to 1, and we're able to prove it by first principle. Now we're going to apply the principle of Pascal triangle to solve this derivative by first principle. So if y equals to x squared, find the derivative of dy dx. That's find dy dx. So normally you have y equals to x squared dy over dx will be, when you are differentiating this, we are asked to 2 times 1x 2 minus 1, which is because dy over dx equals to 2x 2 minus 1 is 1, so it's 2x. So dy, when y equals to x squared, dy dx equals to 2x. So we want to prove this by applying first principle. Right. We were able to prove that if y equals to x squared, dy dx is 2x. Now I want to apply the principle by first principle using Pascal triangle to prove that if y equals to x squared, dy dx equals to 2x. So by first principle, you have y plus dy. Y plus dy is, we are going to have, by first principle, this is to power 2. So we're going to use the second phase. When it is power 2, we have 1 to 1. So we are going to have x raised to power 3, 2 with a quotient of 1. Then we are going to have plus 2. The power of x is reducing, we are introducing dx. So x raised to power 1 dx raised to the power 1, then plus 1, this one, x now raised to the power 0, and dx raised to the power of 2. So we're able to apply this. This is the 1, this is the 1, 2, 1 here, because it is power 2. So we want to take y to the other side. So we are going to say dy will be equals to x squared plus 2x dx plus anything raised to power 0 is 1 dx squared minus y. But recall that from our question, y equals to x squared. So we're going to put x squared in place of y. So dy now becomes x squared plus 2x dx plus dx squared minus x squared. Remember, y equals to x squared. So this one goes with this one. X squared minus x squared goes. We are left with what? Dy equals to 2x dx plus dx squared. So take lim dx tends to 0. Take lim dx tends to 0. So anywhere dx is tends to 0. So this one tends to 0. So we have dy equals to 2x dx. So if we are dividing both sides by by divide through by dx. I'm going to have dx. I want to have dx. Yes, so dx cancel dx. So dy over dx, dy over dx equals to 2x. You can see that we've proved that by first principle that dy over dx when y equals to x squared is 2x. We've gotten the same 2x. So thank you very much for listening to our classes for today. Keep watching and keep subscribing to the channel. More videos will be coming for this week. Thank you very much, listeners, and bye-bye.